well, we're going to continue on with what we did. So I didn't send out a whole lot of homework. Oh, let me put the recording on without being reminded. I'm proud of myself here. I only sent out a couple homework problems because last time we kind of just got just general concepts and some definitions going. But does anybody have a question on any of the homework before we get going? All right. So we're going to do 3 things tonight, getting rolling on all of this stuff with infinite series. So we're going to be concentrating on infinite series for the chapter. That's where we're going here. So we're going to do a couple things.
What is this shit?
All right, so first I'm going to look at a particular kind of infinite series that comes up in lots and lots of different places. And although it's surprisingly easy, as a matter of fact. So we're going to start out looking at something called a geometric series. So a geometric series looks like this. I'll give you the general form. So going all the way out to infinity, we're going to be adding up an infinite quantity of terms. And you can start anywhere you want. Whoops, Jerry's coming in here. Hang on a minute. So the starting point to infinite series is almost irrelevant if you're just looking at it in just general abstract terms. If a series is going to converge, which means add up, where you start isn't going to change that. If a series doesn't add up to something, if it converges, shoots off to infinity, changing the starting point isn't going to suddenly make it add up. So for infinite series, we're really concerned with what happens way out towards the end, even though there is no end. So a geometric series looks like this. So A is a constant, and R is something called the common ratio. I'll show you what that is. So I'm going to write out some of the first few terms. So if n is 0, r to the 0 is 1. So we get a plus ar to the first plus ar to the second plus ar to the third plus dot, dot, dot. And we just keep going. So a geometric series is defined as, to get from one term to the next, you just multiply by r. So AR times R is AR squared. AR squared times R is AR cubed. And we just go out and we go on in here. And R, the letter R stands for common ratio. So it's the ratio. So it's the R that stands for. And that's the number that we multiply by. And it's called ratio for this reason. If we take 2 terms that are adjacent to each other, consecutive, and we divide the one on the right by the one on the left. So for example, these 2 terms. So if we have AR cubed and we divide by AR squared, what do we get if we divide AR cubed divided by AR squared?
AR, or just R?
Just R, that's right. The R's cancel out. I'm sorry, the A's cancel out. And there's 2 R's down here, that cancels out 1, so you get R. But that doesn't happen just with those 2. It happens if you take any 2 terms next to each other and divide the one on the right by the one on the left, you'll always get R. So times R times R times R times R. So these come up a lot. These come up in finance, they come up in biology, they come up in electrical engineering. These geometric series show up a lot. So let me give you an example of an infinite series, of a geometric series here. So let's let A, so here comes an example. If we let A equal 0.3, and we'll let R equal 1/10. Okay. Then our series becomes this. So we get, starting with n equals 0 to infinity. So we get 0.3 times 1 over 10 to the nth power. So when n is 0, 1 over 10 to the 0 is 1. We get 0.3 plus what comes next? Now we have a 1 here. We've done n equals 0, so we go to n equals 1. What's the next term? We get 0.3 times 1 over 10 to the first power. And Nakshan got it 0.03 plus. Now n goes to 2. So 0.3 times 1 over 10 to the second. What comes next?
0.003.
0.003. Oh, now we don't even need this anymore. We can tell what's coming next. Plus 0.0003, and we go forever. We just go all the way to infinity. This adds up to something very familiar. What does this add up to? So it adds up to, if we're adding these together, we get 0.3 plus 0.03 plus 0.03. So we get this. And what does this add up to? We're going to infinity. Something you learned in grade school or middle school. So what? What?
A third.
Yeah, so this adds up to 1/3. So somewhere along the line, you were taught that 1/3 is a repeating decimal, 0.3 repeating. And here we see that that's happening. So here's a case where, so because we added up to a number, this series converges. To converge means a series adds up to a number. It doesn't matter what the number is. Number can be 1/3, can be 0, can be -2. It can add up as long as it adds up to a number. So here's an example of an infinite series in operation and something very, very familiar. So it turns out, knowing if a geometric series adds up to something, you can tell if it converges just by looking. So I'm going to give you the rule for when a geometric series converges. First, unless questions so far on this? All right.
Why is it called a geometric series? What's geometric about it?
Well, if we were in a classroom, I would show you an animated PowerPoint to show you why. But it turns out that there is geometry to this. I'll send you something. I'll send you a little PowerPoint so you can actually see how that's happening. It's hard to show on a tiny little whiteboard like this. So I will give you some of that. The pictures are actually kind of cool. All right, so geometric series converges. If and only if the value of R is between -1 and 1. Can't be 1, there's no equal here. So if you're in between -1 and 1, an infinite series will always add up. Another way to write this is to say that the absolute value of R is less than 1. And here's why this is true. If you take a number smaller than 1, like 1/2 or 1/3, and you start squaring it, if you take a number smaller than 1 and you square it, does that get bigger or smaller? 1/2 squared is 1/2 times 1/2, which is what? So 1/2 squared, which gives us 1/2 times 1/2, that equals 1/4. Whoops. That number just got smaller. So when you square a tiny number smaller than 1, the numbers get smaller. So every time we raise the exponent by 1, that number gets smaller and smaller and smaller and smaller. And eventually they go to 0. And that's why this can add up. But only if that. Now, because of this phrase, if and only if, So if your common ratio is smaller than 1, series converges. If your common ratio is not one of these, it's 1 or bigger, it diverges. So this is a yes or no rule. So looking at a geometric series, so we know that if we have this geometric series, let's say 10 times, let's say 10 times 7 over 15 to the n. Because r is equal to 7 over 15, and that is less than 1, this series converges. Done. That's the answer. So throughout chapter 9, for the next couple classes, our goal is to be determining if an infinite series converges or diverges. Now, usually, if it converges, we won't know what it adds up to. There won't be a way to find out. But in this geometric series, there is a way to find out what it adds up to. And in general, we don't care what it adds up to. We just want to know if it converges or not. So converge means to add up to a number. But a way to think about that's better is you have something, if you converge, you become stable and you just kind of stay there. If you diverge, you kind of shoot off to infinity, or you just keep bouncing up and down. So that's the rule for geometric series. You just do it by looking. What was I going to say? Oh, so geometric series. It turns out we can figure out what a geometric series adds up to all the way to infinity, and it's a surprisingly easy thing to do. So if your common ratio, if the r is less than 1, between -1 and 1, then this infinite series adds up to, this simple formula right there. That's all it is, and you know what that series adds up to. Surprisingly simple and kind of useful. So I'm going to give you an example of how this works. So I'm going to use a different board. Here's an example of a sum. So let's let A equal 0.6. Well, no, let's let A equal 2/3. And let's let R equal 1/10 again. So our infinite series looks like this. So 2/3 and 1/10 to the nth power. Since 1/10 is less than 1, the series not only converges, but it's going to add up to this. So A is the constant, 2/3. And on the bottom, we have 1 minus 2/3. So I've just applied these two to this sum formula right here.
Isn't 1 minus r?
Isn't that what I wrote?
Isn't r 1/10?
I'm sorry, what?
Isn't r 1/10?
Oh, 1/10. Thank you. Yikes. Yeah. I don't know why I wrote that. Thank you. Okay. So this becomes 2/3 over, well, 1 minus 1/10 is 9/10. When you divide by a fraction, you multiply, times 10 over 9. Whoops. Wait a minute, did I do that right? My brain froze up.
It would be 10 over 9, right? Multiplied by that.
Yeah, it would be 10. My brain froze up there for just a minute. All right. So let's see. We got some do we have canceling out? No, we don't. Hold on. Why am I? My brain just hit a pothole and crashed, because this should come out to Oh, I know what I did wrong. Hold on. I know what I did wrong. I know what I did wrong. Hold on just a minute. Actually, I'll tell you what I did in just a minute. So I'm writing down 0.6 here. So 0.6, so up here we have 0.6. Okay. So down here we have 0.6. And then we have over here, there we go. Now I've got it. So 0.6, I can write 0.6 as 6 over 10 times 10 over 9. And this leaves me with 2/3. That's what I meant to do. I wrote down the answer for A instead of what I wanted. So this series, if we wrote this out, this is 0.66666, just like the one we did before with 0.3 here. And so we know that 2/3, another way to write that is 0.6 repeating. So everything canceled out here and we end up with 2/3. Yeah, I wrote down the answer instead of what I meant to do. So let's do another one because I messed that one up a little bit. So let's let A equal 3 and we'll let R equal 2/5. 2/5 is less than 1, so this series will converge. So we got infinite from n equals 0 to 3 times 2 over 5 to the n. So this is going to give us 3 plus 3 times 2/5 plus 3 times 2/5 squared plus all the way out. Because this is less than 1, this will add up to A over 1 minus R. So that's going to be 3 over 1 minus 2/5. So that's going to be 3 over 3/5. And so that's going to be 15 over 3, and that will equal 5. So this infinite series adds up to 5, but only if you go all the way to infinity. So finding the sum of an infinite geometric series, you can tell if it converges just by looking. If this number is less than 1, yes, it converges, and it will actually add up to that number right there. So these come up a bunch, so it's nice that it's so easy. But not every infinite series is geometric. Mostly the series we have may not have a discernible pattern to it. So we're going to look at a general infinite series. And they just look like this. This is what you'll see in the book. There. Now it looks like something's missing. What does it look like is missing?
Where n begins.
Yep. And the reason that you won't see this here is because it doesn't matter. It doesn't matter where you start the index at. If this series is going to converge, if it's going to add up to something in an infinite series, it's going to add up to something no matter where you start. Where you start will just change what it adds up to, but it won't change what it adds to. And if an infinite series is going to diverge, you can't make it stop by changing the starting point. If you have a series that's shooting off to infinity, you can remove the first 300 million terms. It's still going to go to infinity. So our job is to figure out, will this add up, converge, or won't it? So we're going to be learning over the next couple of classes a number of tests that can be applied. And the first and most, well, not the most important, but the first test we're going to look at is something called the nth term test. We're going to look at what happens to this as we get out towards infinity on here. And I'm going to write the test in 2 different ways. So first of all, it should make sense that for an infinite quantity of numbers to add up, those numbers have to get really, really, really small. If you add up an infinite number of big numbers, you're just heading off to infinity. But if those numbers get small enough, fast enough, they begin to look like zero, and they will cause that thing to converge. Like I showed you in the last class, I wrote that circle on the board, the pizza, and we kept slicing things in half. And we realized if we sliced them infinitely enough and they kept getting small, it would still add up. Or the little picture I drew of one person throwing a tennis ball to somebody else and had to pass a number of halfway points and it still gets there. It converges over here. So the way the test is phrased like this: if your infinite series converges, then the limit as n goes to infinity of your terms has to be zero. If you've got an infinite number of terms going out here, then the terms eventually have to look indistinguishable from zero so that you're not keep building these things up. So this is the way the test works, but we can't use the test this way. This just says if we already know a series converges, then we know the terms eventually look like zero and stay that way for infinity. But to do that, you have to already know if it converges. So we're going to use the test in a different way. So I'm going to take a little break here. And what we're going to do is rearrange these. I'm going to change these two terms around, but there's a logic rule that we have to pay attention to first. So a little sidetrack to logic here. All right. So in logic, a phrase that's an if-then statement called a conditional statement, there's an arithmetic, there's an algebra to how language works. So if it's a dog, then it's a mammal. Do we all agree that's true? Right? Every dog is a mammal. So if that animal is a dog, then it's a mammal. Now, can I switch these around? So we have something called commutativity, or for Kayla's benefit, reflexive. Commutative. If 5 plus 7, does 5 plus 7 equal 7 plus 5? Is that statement true?
Yeah.
Yeah. So addition is commutative, doesn't matter which order, but not everything. So this is true, but not everything is true. 10 minus 3 is not equal to 3 minus 10. Subtraction is not commutative. If-then statements, if I did a commutative thing here, if I swap those around, so we agree that this is true. If I write, if it is a mammal, then it is a dog. Is that statement true?
No.
No, not true. Could it be a dog? If I told you I have a mammal behind my couch, could it be a dog?
Yeah.
It could, but it doesn't have to be. So that statement is false. However, if I put the word not into here, if it is not a mammal, then it is, finish that sentence for me.
Not a dog.
Not a dog, very nice. Aha. So there's rules to an if-then statement. If it's a dog, then it's a mammal, is just another way of saying, if it ain't a mammal, it ain't a dog. So there is a rule to how we can switch these things around. So for those of you going into discrete math, eventually, this is the kind of stuff you do in discrete math. So let's go back to our little rule here. So we can't just reverse this. We can't say if the nth term goes to 0, it converges. We can't say that. That's like saying every mammal is a dog. Maybe, but maybe not. So how we use the test is we put it into this usable form if the limit is not 0, then finish that sentence for me. It's the mammal dog thing all over again. If this is not 0, then
It doesn't converge.
it doesn't converge. It's not converging. And the word for not converge is,
Divergence.
there we go. These two statements say the same thing. This one's not very useful when we're trying to test a series. This one is. So think about it like this. Whenever it rains, there has to be clouds in the sky. You can't have rain without clouds. So if you're in a building, you're in a room, and there are no windows anywhere, and somebody comes into that room and tells you it's raining, you don't need a window to know that there's clouds up in that sky. If somebody comes into that room and tells you there's no clouds in the sky, you don't need a window to know what?
It's not raining.
Not raining. If somebody comes into that windowless room and tells you there's clouds in the sky, what do you know?
That there's clouds in the sky.
Yeah, and you know that it might be raining, but you can't be sure. How would you have to be sure? You need to go find a window and look out it, right? So that's how the nth term test works. If this limit doesn't go to 0, done, that's it. Series diverges, move on to the next problem. If this does equal 0, then you know that that series might converge, and you have to go and figure out another way to do it. So the nth term test is the first one to look at. So the nth term test can only tell you if a series diverges. It can't tell you if it does converge. It can only tell you maybe you have to go do some more work. So here's an example. Here's our infinite series. So there's our series. That's the nth term right there. So I'm just going to write out the first few terms just for practice. So when n is equal to 0, we get -4/2 plus. And then we go to n equals 1. If n is equal to 1, we get -1. And if n is equal, we get -1/7. When n is equal to 2, so we get 2/10, we get 2/12 plus. Okay. From here to here to here, what's happening to my terms? Are they getting bigger or are they getting smaller? Terms
Bigger.
So here we have -2, right? -2. Then we go to -1/7, which is bigger than -2. And then we go to +1/6, which is bigger. So these three terms, this term is bigger than this one, this term is bigger than this one. So it seems like our terms are getting bigger, but that's not enough to say it because we got to go all the way to infinity. And who knows if 50 million terms that way, maybe everything starts getting smaller. So we apply the nth term test. We look at the limit as n goes to infinity of 3n minus 4 over 5n plus 2. Now, we could change the n's to x's, and we could apply L'Hopital's rule. That would be fine. But I'm going to give you sort of a more intuitive way to do it. So the derivative of the top would be 3, derivative of the bottom would be 5, and we would get 3 over 5, which is not 0, which means that series diverges. We are done with that problem and we move on. Now here, instead of using L'Hopital's rule, we could think of it this way. As n gets really huge, I mean really big, like a trillion. If you put a trillion in here, you get 3 trillion minus 4. Then you get 5 trillion plus 2. But is 5 trillion plus 2 really different than 5 trillion? As n gets big, does this minus 4 and plus 2, do they really contribute anything at all? Not really. Yeah, as n gets bigger and bigger, these constants just kind of become meaningless. If somebody owed you $1,000 and they showed up at your house one day with a suitcase, thank you so much for loaning me that money. I can't even tell you, it just made life easier. And here's your money back. And you counted it all up, and there was $999. They were $1 short. And would that really be a big deal to you? Isn't $999 pretty much $1,000? Well, depends on your personality, I guess. But so this, everything kind of cancels out. So that diverges, that's it. And you move on to the next problem. So here's another example of the nth term test. And I'm not even going to put this down here because the starting point just doesn't matter. So let's do x minus 9 over x squared. Let's see. Okay. So we look at the limit as n goes to infinity of x minus 9 over x. Oh, sorry, these shouldn't be x's. I'm sorry. These should be n's. The difference, oh, by the way, the difference between n and x. And these series are in fact functions, because you put one n in here, you only get one number back out. So here's the difference in notation. And here, if you see an x, that tells us that our domain are real numbers. So into a function f of x, you can put 2.7, -5, pi. But when you see n, a function in n, we're only looking at integers. So n for these problems, n will be 0, 1, 2, 3. So we're only putting in non-negative numbers into here. That's the difference. A function of n is a subset of a function of x, but for series, all the inputs are numbers. And it'll be that way all through chapter 9. Okay. Now, if we plug infinity into here, we get infinity over infinity, which doesn't tell us anything. That's an indeterminate form. So that's not enough. So what can we do here? How can we figure out what this limit is? What's one thing we could do?
factor n squared minus 49, and then you can cancel out the n minus 9.
So n squared minus 49 is n plus 9 times n minus 9, difference of two squares. And the n minus 9s come out and leave us this. Now, if we put infinity in here, we get 1 over infinity plus 9, which is 1 over infinity, which is 0. So the nth term went to 0, so does that mean this converges? And the answer here is no. This just tells us that there's clouds in the sky. As we go to infinity, this expression, as we get far enough out into infinity, the terms begin to look more and more and more and more like 0. So they're getting smaller and smaller and smaller. That just tells us there are clouds in the sky. So here, we can't say that it diverges, but oh, wait a minute. Shouldn't 49, everybody see Nicholas's comment? That should be 81, I'm sorry. Thank you, Nicholas. My original thought was 7s for some reason, sorry about that. And Hannah, you were right there with me. You must have been looking in my messy brain or something.
Yeah, sorry.
Don't be sorry. Makes me feel better I wasn't the only one. So all that tells us is, does it converge? Well, this just tells us maybe. It's a possibility. So we will have to go and do something different to find that out, which we're not doing tonight. And by the way, the answer is no, it diverges. I can tell just by looking at that. And in the next class on, what's today, Tuesday, on Thursday, you'll be able to tell just by looking at that as well. So the nth term test definitely can tell you if something diverges, but it can't tell you converge, it can only tell you maybe. Turns out this one actually does diverge, but we'll get into that later. So nth term test. The first thing you should do for any series is, we're back to this, is look at the nth term. If it does not go to 0, then it diverges. If it does go to 0, we'll have to use some of the other tools that we have. Okay, so far tonight, we have geometric series. And we're in section 9.2 of the textbook, by the way. And we have the nth term test. There's one other thing I'm going to show you tonight that we need, or will need. We're going to look at factorials. And the symbol for that is that exclamation point. Now, I know a bunch of you already know what these are, I'm assuming. And I also figure there's some of you who maybe haven't seen these before. If you've had a class in statistics and probability, you've seen factorials. So let me just tell you what factorials are. Let me give you an example. So 4 with an exclamation point. This exclamation point is an instruction. It tells us to do something to that number in the same way like the square root sign tells you to do something to this number. And this means 4 times 3 times 2 times 1 is 24. That's what 4 factorial is, 24. If we have 7 factorial, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and that equals 5,040. Just multiplying them all together. So it's just a definition here. But these are going to come up in a lot of our series. And those of you going into differential equations, factorials come up a lot in something in something called Laplace transforms. You'll see factorials coming up a bunch. So what we got to do tonight is simplify some things. We need to handle the algebra of factorials. But before I go on with that, just in case you haven't seen factorials, not to do with this class. Factorials come out of a branch of mathematics called combinatorics. Combinatorics is a fancy way of counting. So how many different ways can something happen? Comes up in probability a lot. So we count things, and factorials count permutations. Another word for permutation is like a rearrangement. Okay. A rearrangement or shuffling things around. So for example, if I have three objects, if I have a square, a triangle, and a heart. So N, I have three objects. One way I can shuffle these around would be to write it as a triangle, a heart, and a square. What's another way I could rearrange those three objects? A different way.
Heart, triangle, square.
Heart, triangle, square. Is that it?
Heart, square, triangle.
We could do heart, square, triangle. Are we done yet?
Square, heart, triangle.
Square, heart, triangle. All done? We get them all?
Triangle, square, heart.
Triangle, square, heart. We all done? Not sure, are you? And this is only three things. Is there any other way to shuffle those around? Counting is hard, isn't it? And this is only three things. The answer is no. That's all there is. How many are there?
6.
Yep, 1, 2, 3, 4, 5, 6. And 3 factorial is equal to 3 times 2 times 1 equals 6. That factorial counted how many ways there are to take three things and shuffle them around. It's a very fast way of doing that. So if we change this to 5 objects, so heart, square, triangle, oh, now I'm stuck for a shape. Circle and star, okay? If we started to count how many ways there are to rearrange these, think we get them all? No. The answer would be if we got them all and got them correct, we'd have 120 different rearrangements of those. That's a lot. That's why pin numbers and things work, because there's just a lot of ways to shuffle things around there. So factorials are a way of counting permutations, which isn't something we're doing in this class, but I wanted to let you know that's what factorials can do. So those of you who've had probability before, factorials come up a lot when you're figuring out how many ways to rearrange some people and test medication on them or something. Okay, so simplifying factorials. So if we do, for example, 5 factorial over, no, I don't want to do that, change my mind. Let's do 4 factorial over 6 factorial. Now, ordinarily, if we just had that fraction, what does that fraction simplify to?
Over 3.
It just factor, right? That's just 2/3. But this doesn't work the same way because that's not a 4 and that's not a 6. This is 4 factorial. 4 factorial is 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But since everything is being multiplied, that means everything is a factor, and we can cancel. Those cancel out, and what we're left with is 1/30. So that simplifies to 1/30. So this is just basic manipulation of factorials. So what we can see here is 4 factorial is 4 times 5 times 3 times 2 times 1. And I can write 6 factorial as 6 times 5 times 4 factorial. So this 4, 3, 2, 1, I've just left in its factorial form, and those cancel out and put me back at 1/30. So these aren't particularly difficult, but if this is brand new to you, it looks a little mysterious, and that's why in this section there's a little bit of practice on this, because these will come up later, not so much in this section. But we're not going to have numbers. We're going to have some n's on here. So our factorials look like this. So the definition of factorial, n factorial is equal to n times n minus 1 times n minus 2 times 3 times 2 times 1. You start with a whole number and you multiply every number reduced by 1 all the way down until you hit 1. That's kind of the definition of a factorial right there. So example, if we have n plus 1 factorial, and on the bottom, we have n plus 3 factorial. And we want to simplify that. Now remember, n, our values for n are not negative. They can be 0 sometimes, sometimes not, but our n's aren't going to be negative. So if n's not negative, which of these numbers is bigger, n plus 1 or n plus 3?
N plus 3.
So when we cancel out, our top is going to disappear. So I'm going to show you how to I'm going to do a couple of these examples. So on the top, we have n plus 1 factorial. On the bottom, n plus 3 factorial would be n plus 3. What's 1 less than n plus 3?
N plus 2.
Right, n is a number. So next would come n plus 2. And what's 1 less than n plus 2?
N plus 1.
Plus 1. And then would come all the rest, but I can write that as factorial. These cancel out. And this simplifies to 1 over n plus 3 times n plus 2. That's the simplification. As n goes to infinity, that goes to 0 because all the n's are down below. So let's see if this worked. Let's actually try something here. So for this problem, I'm going to pick an n. So let's say that n is equal to 3. If n is equal to 3, 3 plus 1 is 4. If n is equal to 3, 3 plus 3 is 6. And we already know that this reduced to 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1. they cancel out and we get 1 over 30. So 1 over 30, now if we look at this, n was equal to 3. 3 plus 3 is 6. 3 plus 2 is 5. We get that. And this turned into 130 when n is equal to 3. So it works. So this probably looks a little mysterious if you haven't seen this before. So that's why there's a little bit of practice in here, and we'll see these again. So I'll do another example that looks like this. Oh, questions on this at all first? All right. So let's simplify, let's see here. N plus 3 over n plus 1 factorial n factorial. All right, so we're going to simplify this. So what's bigger, top or bottom?
Top.
Top is bigger because of the plus 3 and the plus 1. So on the top, so here I'm just going to keep the smaller number here. On the top, by definition, n plus 3 factorial is n plus 3 times 1 less than that, which is 3 minus 1 is 2, n plus 2, times 1 less than that, which is n plus 1 factorial. These cancel out. This leaves us with n plus 3 times n plus 2 over 1. And now the limit as n goes to infinity of this, well, we get infinity over 1, which is just infinity, so that diverges. If we put infinity up here, we get infinity over infinity, which we don't know what that means, but by doing this little bit of manipulation, we end up, in this case, there's no n's in the denominator, only the numerator. So as n goes to infinity, this whole thing just shoots off to infinity. So that's probably new to most of you. It just takes a little bit of practice, which there will be in the homework. And that will come up not on Thursday. We'll see more of this next week. So this is all very different than chapter 7 and chapter 8, right? We're not spinning rectangles and making discs and washers. We're not doing by parts or trig sub. It's a whole different way of thinking here. So here's what we did tonight. Geometric series. We did the nth term test, which can only tell you divergence. And we looked at how to manipulate factorials a little bit. That's kind of a lot for one night, I think. So has anybody got any questions about anything? Anything at all? Well, all right then. I am recording this. I'm very proud I remembered to do it all by myself without being reminded. I'll upload the recording and I'll put some homework up in files, and on Thursday we'll go over whatever we need to go over, all right? All right, everybody. I'll see you back on Thursday. Kayla, good luck with the rest of your homework. If you want to give me a call or something after class, I don't know if I can remember all that stuff, but I might just confuse you, but it's up to you if you want to give me a call.
Thank you. I'm gonna keep working on it for a little bit.
Yeah, that's probably a good idea. I'll probably just like screw you all up and yeah. All right. I'll see everybody on Thursday. Good night.
Bye, thank you.
Thank you.
Professor,
Yes.
I have a question about my test.
Okay.
I was just wondering if, like, you could tell me which problems I got wrong in, because.
Sure. I'm going to send out a solution sheet, but I have to wait like a little bit. There's a couple of people in the class. I don't remember if this class or not, who had some sort of like life stuff happen and they needed just a little bit of extra time.
Okay.
But if you want, I don't remember offhand because there were like 60 tests that I graded. But if you want to set up a one-on-one Zoom, we can go over it if you want.
Yeah, can we do that?
Yeah, what's a good time for you?
Um,
So tomorrow, I have a class tomorrow. I have 2 classes tomorrow. I start at 11 and I'm done at 2.
I get off at work around 5:30.
Oh, so you want to do it tomorrow night?
Yeah.
So
Would
you
like 6 o'clock be okay?
get off work at 5:30. Don't you want to like go home and like do whatever you do to relax? You can make it later if you want.
What time, like, because I don't want to keep you too late.
I'm not going anywhere. If you want to do it at midnight, I'll do it at midnight. No, I'm not even joking. I am up at all. So whatever is comfortable for you. I have no plans at all tomorrow or for the rest of my life, apparently. So
Is 7 o'clock okay?
7 is great.
Okay.
Meet you here on Zoom at 7. Same ID, same password.
Okay. Thank you so much, Professor.
All right. Thanks a lot.
Thank you. Bye bye.